Okay, guys, welcome back to class number 3 this week. We're working our way through chapter 4, and we're going through practice problems for calculating particles or formula units or grams mass, for example. So yesterday we didn't get to do this example, so I'll very quickly show you the workings for this. And then we will go into this new one. I just wrote this one, so this one isn't in your notes that are on the D2L. I just kind of made it up. Okay, so let's go back to look at this problem. How much mass, so that's M, would 5.1 times 10 to the 25 atoms of zinc have? So atoms, remember guys, atoms, formula units, molecules, these are represented by the letter N, uppercase N. So I have to do a couple things here. First thing I need to do, well, okay, let's write down my formulas here. I know that the number of atoms would be equal to the moles of the chemical times Avogadro's number. But I have a problem. The problem I have is I don't know moles. So what I need to do in my first step, once you get the molar mass of zinc, oops, sorry. Oops, sorry, I'm writing this wrong, my bad. My bad, ignore me for 1 second. We'll go, pretend I never said that, I just wrote the wrong formula, but I guess my point still stands. Sorry, we're looking for this formula. But the point still stands that I have a problem. I do not have moles. So what I would do first is use my other equation. Because I'm given particles or atoms, I can use this equation to calculate moles, and then I can put it into my second equation. So we're using two equations here. The first equation is to find moles, and then the second equation is to put it into my mass formula. So step number 1, right, I would find moles by taking my particles and dividing it by Avogadro's number. Again, I had a student yesterday ask me where this number comes from. It is a constant. So like gravity or pi, this number is a constant, and it's in your data booklet. Okay, so I found my moles, 84.6895. Next, I need to do step number, I guess arguably step number 2. Here, it's not much of a step. Step number 2, if you want to find the mass, you will need moles and molar mass. So step number 2 is to find the molar mass of my compound. Now, the good news is this is very simple because we're just dealing with zinc. We don't have to calculate anything. You just go to find zinc on your periodic table and write down the molar mass. It's not zinc 2 or zinc 3 or anything like that. All right, and step number 3. And no problem if you're late, I don't mind at all. Step number 3 is to calculate the mass. So mass is moles times molar mass. So I just take my two answers from step 1 and step 2 and multiply them together using this formula. Really, the only challenge here is making sure you know your formulas and you know how to rearrange them and use them. So let's do that example that I asked you guys to try at the beginning of class. And if anybody was late, you maybe missed this, but I just wrote this problem for you guys to practice, and we're going to do this together right now. And I don't have the answer, meaning we're going to work through this step by step. And this is very much wink, 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 like a question in your lab or a question that you would see maybe on your final exam where it's a 3-step problem. So before I do anything, let's make a plan. What I mean by that is let's just kind of organize what the question is looking for and what the question is giving us. So the question is looking for formula units, or N, and it's giving us mass. So the first thing I would do, like, okay, let me write on the bottom here. What the question is asking me to do is calculate my number of formula units. And to do that, I need this equation here on the bottom of the screen. There's a problem though. I can't do this equation until I find moles. So the first thing I would do would be to calculate moles using my mass over the molar mass. And then you just take whatever your answer is. Oops, not a very nice line. Another not a very nice line, and then put it in here. So arguably, this is a two-step problem. Find moles, put it into my equation. But there is another step here. I need to find the molar mass first before I can do the first calculation. I have a question in the chat about the letter N. N can be atoms, N can be molecules, N can be formula units, N can be particles. N can actually be anything. Like I mentioned the other day, N could be stars in the universe. N could be grains of sand on the beaches in the world. N can be anything, but in chemistry, N is typically atoms, molecules, formula units, or particles. Formula units, guys, are what we call ionic compounds. Molecules are what we call covalent compounds. All right, so anyways, I'm going to actually, this is going to sound weird, but I'm going to clear my screen and we're going to do this together. Okay, obviously I don't have any room to write here. So let's do this. Step number one, before I can do this equation, I need to find molar mass. So I'm going to clear this. Don't worry. I'll have this kind of written out again. I'm just going to go through this step by step. Okay, here we go. Step number one, molar mass. Let's pick blue. I've been feeling the color blue lately. So step number one, molar mass of FeCl3. Okay, this is pretty simple. I'm going to open up my periodic table. I had it open. I got to open it again. Sorry, I got another computer screen here, so I'll just open it here. Okay. All right. So I'm going to add together the mass of iron. And just like Aman says, I'm going to add together the mass of iron plus 3 chlorines. And Abdul Rahman might have my first part of my answer here. So let's just see. So iron, 1 iron. Oops, my bad. Sorry, guys. 55.845. Okay, and I'll add that to 3 times my chlorines, which is 35.453. Okay, and if you were doing this on a calculator, like a nice calculator, a scientific calculator, you know, a Casio or TI-83, you can just do this in one big step, which I'm going to do. So I'll start with the 3 chlorines. And I get 162.204 grams per mole. Now remember, molar masses are typically large numbers. So when you guys are calculating molar masses, you should get a number between, you know, well, 0 and 500. If you get something like 0.0002 something has gone wrong. Typical molar masses are like 20, 30, 40, and up to about 200. But you can get them in the 300s. I've seen that before, some larger compounds. Okay, step 2. Now I can calculate my moles. I have to use this equation to calculate moles because the only number that this question is giving me is the mass. So 1.25 grams over 162.204 grams per mole. Okay, so let's do that. Okay, and I get, oops, how did I mess that up? Sorry guys, my finger must have not pressed the right button there. There we go. All right, let me just check the chat too, see how everybody's doing. Yep, Abdul Halim is correct. Aman is correct as well. 3 decimal places for our significant figures. Oops. Now, realistically, I'll show you a significant figure trick at the end, but Aman is correct. We're adding these together. So we take 3 decimal places. All right, so the next answer. I will get, pick blue again, 0.00. If your calculator gives you scientific notation, that's fine. 77063 MOL. Now, some of you guys might be thinking, hold up, this is way too many significant figures. I only have 3 significant figures. But the rule is we round our significant figures at the very end. Okay, so I'm not going to round to 3 significant figures until step number 3. And step number 3 is nice and easy. Step 3, my formula units is my moles times Avogadro's number. So 0.0077063 moles times Avogadro's number, which is a constant, like gravity. My computer's being a bit slow here today, but anyways, no big deal. So I'm almost done. I'll check the chat in a second. I see some comments going in there, but I end up getting formula units per mole times by moles. The moles cancel. So my answer will be the perfect units. And let's see what I get. So times. Make sure if you're doing this along with me, you use your exponent button on your calculator. And I end up getting 3 significant figures, 4.64 times 10 to the 21 formula units. All right, there we go. That's it. That's the problem. It would be, if you did this on a test or, in your lab, it would be worth 3 marks, maybe 4 marks on a final exam. But it's basically a mark per step. All right, let's check the chat. No. Like when one of the questions was, are you going to have to type all this? No, the only thing when you do this this is kind of unfortunately, when you do this on a test, oops, you just do this, you just enter your answer. So we'll try to set it up so you guys can do it like a step at a time, step 1, step 2, step 3, but you would only enter the numerical answers. You don't enter the you don't type everything out. You just put in the numerical answer. Whew, okay, so guys, the good news is for the rest of today and probably most of tomorrow's class, we can take a break from the numbers now. We don't need to worry about the numbers. Oh, sorry, I forgot to mention that as well. I'm just reading the chat there. The trick, I mentioned that I would show you a trick at the end, and the trick, maybe it's not as exciting as I made it sound, but it's a significant figure trick. If you're ever confused or you don't know what to do for significant figures, look at the question. The smallest number in the question, 99% of the time, like I mean, almost every time, I can't think of many situations, but 99% of the time, the significant figures in the question will be the significant figures in your answer. So let me just get a different color here. I'll go with green. If this number has 3 significant figures, then my answer will have 3 significant figures. It's not much of a trick, but I promise you it will save you guys a lot of time. Instead of worrying about significant figures, you just look at the question. The smallest number in the question will be your answer. And then you don't have to worry about significant figures as you're doing your calculations. Just make sure the last answer has 3 in this case. Okay, so like I was saying a minute ago, as Abdul Halim says in the chat, there's no more math for today or tomorrow, well, most of tomorrow. We get to kind of take a break now, and it might be a little boring, but we're going to talk about basically just a list of different definitions. I taught it this morning with the other group. It is a little bit boring, we'll say, but it is useful. I'm going to explain to you a couple of definitions. Hiba in the chat asks, when is test 2? Test 2 will not be next week. It will be the week after. I don't know what day, because I have to talk to the other chemistry instructors, but the test number 2 will be in week 12. So between November 15th and the 19th. But I don't know the day. Again, I think there's at least 4 other sections of chemistry. 2 of them are mine, and then 2 are with other instructors, Michelle and Mohammed. So I have to talk to them. We don't know. It'll probably be, Wednesday or Thursday or something like that. And it will be, Aman, it will be the same as test 1. You can do it at any time in a day. So say it was Thursday or Wednesday, just like test 1, anytime that day. You could do it 8 in the morning, or you could do it 10 o'clock at night. And I'll give you 2 hours again as normal. It's only an hour-long test, but I'll give you double time, just to be safe.
Sir.
Yes.
When the test? Just do, please.
I just said when the test was.
No, I didn't hear. Sorry.
No problem. The test number 2 would be November 15th to 19th, but I don't know what day. So not next week, but the week after. And I'll let you know when the day is as soon as I find out. Okay, I promise.
And from 3.3 until where?
3.3 until at least the end of chapter 4. Again, I don't know the full details yet, but I'll let you know the full details next week.
Okay, thank you.
All right, cool. All right, guys, good questions. You guys always kind of ask me the good stuff. So let's very quickly, it's only 2:55, but let's take a few minutes today, maybe 15 minutes or so, and let's talk about some definitions. This will be a little bit boring, I'm sorry, but this will get you ready for your lab number 8. Okay, don't forget about lab number 7. It's not due until next week, but in lab 8, it's actually one of my favorite labs. Lab 8 will be on campus. I know that's not the best, but in lab 8, we're going to learn a very important chemistry technique. So you kind of need to be there and do it with your own hands. And it's about solutions. So let's look at solutions. These are the outcomes, and you can see, I'm not going to read them all, but you can see the solutions are all just describe, explain, state. There's no calculations here. So there's no math needed in this section. It's just straight up memorizing or understanding terms. All right, so let's go. Here, and again, I do apologize. This is just going to be basically me reading definitions, but that's all we can do. A solution. What is a solution? I'm drinking a solution right now. I ordered, don't tell anybody, but I ordered McDonald's for lunch. So I have a Pepsi in front of me or a Coke. A Coke is like a solution. It's a homogeneous mixture of two or more substances. Now, what do I mean by homogeneous? Well, in my opinion, I think there's a mistake on this slide. I don't think tea or juice are actually homogeneous. I didn't make this particular unit, but I don't think tea or juice are homogeneous. Why? What is homogeneous? And by the way, you might have heard, if you've ever heard this word before, you might have heard other people say homogeneous, homogeneous, homogeneous. It's this, different pronunciations. In science, the word homo means the same, like hetero means different. So a homogeneous mixture looks the same. It looks like one substance. So what are some easy examples of this? Homogeneous. Salt water is a good one, like the ocean. Now, I don't mean if you scoop up ocean water and you get seaweed and fish and dirt. I mean pure ocean water. It's a weird statement to say, but I mean like filtered ocean water would look homogeneous. It would be a mixture of H2O and NaCl and other different ionic compounds. But when you look at a glass of ocean water, it just looks like water. What's another example? I mean, my favorite example might be something like a sports drink, or more specifically like Gatorade. I don't know if you guys are familiar. I know they sell it here, but like Gatorade or like sugary drinks, they look the same, right? If I look at a bottle of Gatorade, it just looks like a blue liquid or sometimes a yellow or orange liquid, but it looks the same. So what would be okay, so Aman brings up a very interesting point, which it's the exact same thing someone brought up this morning, and I can go really deep on this, but I'll come back to you, Aman. That's a really interesting statement. But kind of going back to the energy drink or sugary drink concept, when you buy this, you go to Lulu or Almira or wherever you shop and you buy a Gatorade or Pepsi or Coke, that solution is probably months old or at least a few weeks old because, they make it and they ship it here and then people buy it. But that solution never changes. Now think about something different like coconut milk or cream, like in a can, or labna, or like, really fatty milk things. They tell you to shake it before you drink it, like a pure orange juice or, some different types of juices. They tell you to shake them. Why do you shake them? Well, over time, in things like coconut milk or sour cream, labna, over even like yogurt, over time the mixture kind of separates and the fat might rise to the top, or they kind of split apart. That's heterogeneous. That's not homogeneous. But something like a can of Pepsi, a bottle of Pepsi, I mean, that's good for months or years. It never separates. Aman brings up a very interesting point. Now, you said something more specific. In the morning class, I had a student say oil. And oil is not a very good word because what is oil? Is it olive oil? Is it vegetable oil? Is it oil from the ground, like crude oil that hasn't been refined? Like, what do they mean? Crude oil from the ground, in some cases, is a homogeneous mixture because it's a mixture of hydrocarbons, but it all looks the same. It looks like a big old, black syrup. Aman's example, petrol, I would argue that petrol, which in Canada we call gasoline, but same thing, is homogeneous. And the reason I say it's homogeneous is petrol is not just hydrocarbon. Petrol is also made up of like different fillers and combustion agents that help it burn in your engine, help it burn cleaner. Components, I don't actually know what type of additives they add. So gasoline. Gasoline or petrol is a clear petroleum-derived flammable liquid. I'm just trying to see what else they put in it. Yeah, so sometimes in gasoline to help it burn, they would put things like ethanol in it. So yeah, petrol. Gasoline also contains benzene. It's definitely a homogeneous mixture. Yeah, that's a good example. Cool. All right. Anyways, long story short, I spent way too long just talking about that. A solution is a mixture of two substances, but it only looks like one thing. If you think of something like yogurt with fruit in it, or loose tea, if you drink tea with tea leaves in it, that's not homogeneous because you can see the tea, you can see the tea leaves. In a yogurt, like a fruit yogurt, you could see the white yogurt, but you can also see like raspberries or strawberries. That's not homogeneous. Now, a couple more terms for you. A solution always contains a solute dissolved in a solvent. Now, I'll give you the easiest example I can think of, right? You got your mug of hot water. So in here I have H2O, and I'm going to put in my hot mug a sugar cube. Okay, so if you guys are like me, well, I guess no, I don't put sugar in anything, but if you drink tea or coffee and you put sugar in it, this is a good example of solutes and solvents. The solvent is typically, not always, but typically the substance you have more of. And a really easy way to think about it is, in chemistry, first year chemistry, our solvent is water. The universal solvent is water. So they call water the universal solvent. It's a really good chemical to help dissolve ionic compounds, for example. Sugar, in this case, would be the solute. The solute is the substance that dissolves in the solvent. So salt in ocean water. The ocean water is made up of water and salt, NaCl, and other things. But in the ocean, the water is the solvent, the salt is the solute. In your tea or coffee, the water is the solvent, the sugar that you put in it would be the solute. Okay, so typically the solute is in less amounts. And Aman is getting to a really good point, which I'm going to finish at this point today. If you guys aren't reading your chat, I know some of you, sounds like some of you guys are driving around even. If you can't see the chat, the question is, will there be a level in which the sugar won't be able to be mixed with the tea? And I'm going to finish on that today, and that is a thing. It's called a saturated solution. So I'll get to that in like 5 minutes. That's a really good question. All right. So this slide you don't really need to worry about, but it's setting me up for the next slide. When you guys think of a solution, if you've ever sat in your house and thought of a solution, I don't know if you have, but if you've ever thought of a solution, you might think of them as like a solid being dissolved in a liquid, right? Like sugar or salt being dissolved in water. You might also think of a solution like two liquids being mixed together. So when you mix, say, milk into your tea and stir it up, you might think, okay, well, that's a solution, two liquids mixed. But really, in chemistry, any state, solid, liquid, or gas, can form a liquid with any other state. Now, you don't need to know this slide, but there are two unique solutions that you might not be familiar with. The first solution you might not be familiar with, and I'm almost done for today, by the way, guys. I have this slide, and then I have a couple, like one kind of more topic to talk about. Oops. One thing you might not think about is, what about a solid mixed with another solid? Now, how would that happen? Well, typically when you're making an alloy, you do it under really high heat. So you might melt two metals and put them together. But when they turn back into solids, we call these alloys. And examples of alloys would be steel. Steel is a mixture of carbon and iron. Bronze is a mixture of copper and tin and other things, but mostly copper and tin. So when you mix, or when two solids are mixed in a solution, it's called an alloy. And again, that might be really weird to think about. How do solids mix together? Well, typically what you would do is heat them up very high and they turn into a liquid. You mix them as a liquid and then you cool it into a solid and it would form an alloy. Alloys, for any of my engineering students, alloys are very important. Like the whole concept of steel is really important from an engineering standpoint, because steel is much more durable than just straight iron. So you'll probably learn more about that in another course. Oh, there's more definitions coming. Sorry, someone in the chat mentioned that a lot of definitions. There's a lot more. Anyways, okay. What about if you took a liquid, and you mixed it with a solid and you made, that as a solution? That's called an amalgam. And I'm sorry for the gross picture. An amalgam that they used to use, I don't think this is as common as it used to be, is mercury in silver. So mercury is a liquid, silver is a solid, and when you mix them together, it makes a compound that's safe, and you can use it to fill holes in your teeth, like a dental filling. I'm not a dentist, but I'm pretty sure now they would use things like resins, like plastic tooth-colored resins, or ceramics. It wouldn't be, you don't see a lot of mercury and silver fillings anymore. I mentioned to my class this morning, my father was born in 1950. So he's 70 years old this year. And his back teeth have a lot of these. You can see the metal in the back of his teeth, because in the 60s or early 70s, when he might have got a filling, that's what they used. But for young people like yourselves, and arguably myself, I don't know if I'm that young, but any fillings that we would get would probably be a resin, like a plastic polymer, or ceramic. All right, anyways, this is not dentistry course. Let's move on. I got a couple more things to tell you, and then we're done. I'll finish off with what Iman kind of talked about. So just give me 5 minutes and you're free, because I know it's late in the day. Okay, more terms. I think I have 4 more words I'm going to teach you. So, solubility. Not everything dissolves in water, for example. All right, like think about Qatar, think about the Middle East. If sand, which is typically silicon dioxide, but sand, if sand dissolved in water, there would be no beaches. Qatar would be a much different country if all of the sand was water soluble. So solubility is a measure of how much solute will dissolve in solvent. Some things dissolve, some things don't dissolve. If you guys cook and you put salt in your pasta or rice water, which I hope you do, the salt obviously dissolves. But when you put the pasta in or the rice in, they don't dissolve. They just cook. They, hydrate. So solubility is how much a solute will dissolve in a solvent. And it's dependent on temperature We'll talk about this later in section 4.5 on like how we can modify solubility. Solubilities measured are usually grams per kilogram or grams per liter. Sorry, I just wanted to see something. All right, so typically you would measure solubility as how many grams of solute dissolve in a liter of solution or solvent. And then in the chat, yes, water is definitely a solvent. Again, I mentioned this before. Water is called the universal solvent. Now, it is not universal. It doesn't dissolve everything, not at all, but it dissolves a lot. I think it's called the universal solvent. I might be making that up, guys. Could be some fake news. No, it is not fake news. It is definitely called the universal solvent. I just double checked. I heard that when I was a kid, or maybe a teenager. I heard, oh, water is the universal solvent. Yeah, anyways, it is. So it's capable of dissolving more substances than most any other liquid. So it's really important. All right, so let's look at an example of this. Like, how do we classify solubility? And I'm almost done, guys, don't worry. I'll get back to that question in a second about the acid. So, all right, at room temperature, which this is a little bit warm, a little bit warm, but roughly room temperature, 91 grams of sugar. When you see glucose, just think of the word sugar, will dissolve in 100 milliliters of water. At 50 degrees Celsius, 244 grams of glucose will dissolve in 100 milliliters of water. So you guys notice what's happening? As I'm increasing my temperature, the solubility of the sugar is going up, and we'll talk a little bit more about that later. But this is an experiment you could do in your own kitchen. You could do this right now after class. Get a cup of water, get like I'll say 2 cups of water. At room temperature, put a tablespoon of sugar or salt in the room temperature water, and then heat up the other cup of water, like in the microwave, or you can boil the kettle, and then dissolve the same tablespoon of sugar or salt in the hot water. And you'll notice that the hot water dissolves it much easier and much quicker. So the more we increase the temperature, the more we get the solute dissolving. And again, I'm going to talk about this later in more detail in section 4.5. Okay, 2 slides left and I'm done. 2 slides. And this is it for today. All right, 2 slides. When we are talking, so basically these are words that you need to know for your lab and the future. Like if you do chemistry 1121 or 2420, I'm going to be saying different words to you that you should know. So the word soluble, what does that mean? Soluble means the solute dissolves in the solvent. So it is soluble. What I mean is it will dissolve. So soluble means will dissolve. Insoluble means will not dissolve. So sugar in water is soluble. The sugar will dissolve in water. You guys do that every day if you make tea or coffee. Something like chalk, calcium carbonate, or you could even say, or sand, right? Sand is insoluble. Sand will not dissolve in water. And we're lucky because if sand dissolved in water, like I said, we'd have no beaches. I don't know what Doha would look like. So soluble, the solute will dissolve. Insoluble, the solute will not dissolve. All right, last slide. 2 more terms and I'm done for today. When you mix 2 liquids, it's not really a good thing to say soluble or insoluble, because like when you mix a solid in a liquid, so again, like sugar in water, you watch the sugar disappear. The sugar dissolves into the water. But when you mix 2 liquids, Like again, as Aman mentioned earlier, like in petroleum or petrol, like you put into your car, it's full of, hydrocarbons and things like ethanol. It's not really dissolving. When you mix two liquids together, it doesn't really dissolve. Dissolving is not the right word. What you do is you mix them, and some liquids will mix to form a nice, clean, even solution, and some will not mix. You can see here we have water and oil, right? They don't mix. So we don't like using the words soluble or insoluble for liquids. What we prefer is the words, and I sympathize with you for all these words today, but these are two words I never heard before until I went to chemistry. Miscible, which I always memorize as mixable. So if the two liquids mix together, it would be miscible or mixable. And if the two liquids do not mix together, I can't even speak, we would call it immiscible, which means not mixable. Again, you guys could go do this in your kitchen right now. Depending on what you have in your house, you could do this experiment right now. You could go to your bathroom, you might have something called isopropyl alcohol, or even you guys might have a lot of hand sanitizer around. That's something you could do. Grab some hand sanitizer, mix it with water, stir it up. It should look like the top here. Go to your kitchen, get something like cooking oil, so olive oil, vegetable oil, ghee, even if you have liquid ghee, mix that with water and it should look like this. So when two liquids mix, we say miscible. When two liquids do not mix, we say immiscible. So soluble, insoluble, miscible, immiscible. All right, guys, I am done for today. Aman, two questions before I let you guys go. Aman has some good questions here. One, is acid a solvent? Yeah, acid could be a solvent. In the lab, acid is mostly water. What we do in the lab is we take strong acid and dilute it with water for safety. So acid could totally be a solvent, but realistically, what the solvent is in acid is water. Again, any acid in the lab you use would be almost 95% water. We just put vinegar. If you guys eat vinegar, I absolutely love vinegar. Vinegar is about 6% acid, 94% water. So most acids that you would use in nature are water. Mohammed, I don't think an explosion would happen in your kitchen if you tried this experiment. The last thing I'll mention, and you guys can go, don't worry, is Iman had a question. What if you wrote mixable on the test? If you wrote mixable on the test, I'll tell you right now, the computer will say you're wrong, but I will go through, I did this for test number 1. I will go through everybody's tests and kind of, add some marks if the computer, because the computer is not perfect. Like if you guys spell a word wrong, the computer says you get 0, but I don't really care if you spell a word wrong. So long story short, Aman, if you wrote mixable on a test, I would give you the mark for that. That's no problem. Phew, okay, sorry, I'm gonna hit stop record.